Thank you. Well, today's lecture is on the first of three on simulation. Simulation is the answer to the question, what if? What if we build this? What if we try that? What if we adopt this organization? What if? Now, sometimes a what if is in the past. Something has happened disastrous, and the question is, what if this is what happened? And some of the times it is a simulation to try to find out what did happen by going through what you thought ought to have happened. But it's a very, very general proposition. Now, you always did this. When you wondered whether you should do this or that, you said, well, what if I do this? Well, if I go that way, if I do this, I'll... But they were mental ones. Now we do computing ones because we have enormous computing capacity. Simulation has very greatly risen in importance. And therefore, I'm taking 3 lectures on it. It's one of the main uses of computers one way or the other. What if? Now, the reason computers are better is, A, they're cheaper, they're faster, they're often better, and they can do what you cannot do in the lab. Now, they're cheaper and faster, or easy disposed of. Difficult as programming is, and troubleshooting is, the laboratory is much worse. You will spend much more time struggling in a lab to get equipment going than you will with a program. Now, the other 2 are more interesting. They're often better, more accurate. If I have a missile flying in the sky at White Sands, it's well instrumented, but they can't always tell you exactly where it was and how fast it was going. In a simulation, I've got 5-digit numbers saying where it is, and another 5-digit number telling me how fast it was going. I can get more accurate answers out of a simulation than I can out of real life, particularly in dynamic situations. And secondly, I can answer questions you cannot answer. And I will try and give you some examples of those along the way. That the simulation can answer things you cannot even hope to measure, or things which experiments you cannot do, I can do on a machine. Now, I'll begin with the standard one I always use. At Los Alamos, the first simulation I was involved with was an atomic bomb. And I'm not giving you any great secrets to tell you. One of the designs was circular, and we divided it up into a number of shells. And you remember there was an explosion coming in, carefully designed lenses, so the explosion came in. The shock wave went through and accelerated the parts. But as you see, as a shell comes in, it's got forces on both sides. It's going to be squeezed. But it's being squeezed also, since it's moving into a smaller region, it's going to get thicker. How much thicker? That's going to depend upon the formula between the density and the pressure. We'd like to know just what's going to happen. Well, we get the people who know hydrodynamics and other things, and we get the equations out of Newton and out of hydrodynamics and other things. We have all the equations down there. We get the Hugoniot relations across the shock wave front and so on. And now we simply start. Many shells, 10 to minus 8 seconds. If those are the forces on a shell at that moment, where will it be in 10 to minus 8 seconds? Okay, it's there now. These are the forces then. Where will it be in the next 10 to minus 8 seconds? Straight down the line. Now you can see why it'll work out, because if one of these shells is a little bit too far in, the pressure won't be so great, and it'll tend to fall back as against the push. Now you can see really why it happens. As this gets squeezed down, this front edge must go in much, much faster. As it gets squeezed down, the center part must go rapidly. Then you want to know how long it will stay in when the atomic reaction begins before it blows apart, because if it stays there only a moment, there won't be much. If you hold it in there for a long time, you'll get more radioactivity converted into energy. Now the main point I want to bring across to you is you have to have experts who know how to find the equations. Simulation in the field which you have no expertise won't get reliable answers. And for example, in the area of ecology and so on, when asked to do some problems, I said, how much rainfall produces how much growth, or how much sunshine? How much this gives me how much that? They didn't have any answers. I wasn't going to simulate without some numbers, so they went and found somebody else who would. I simulated more hard engineering ones, where I had definite questions, definite formulas. Now I want to contrast that with the atmosphere. Given the weather, we divide the atmosphere up into a couple layers, and we also divide it into blocks. On each block, there's pressure from all the sides. There's the albedo, which controls how much sunlight will fall on it, how much hotter it will get. There are various other forces. Again, you go to the expert and you get all the formulas acting on this, so you ask yourself, what will happen to that block in the next length of time you want to use, say hour. And you track all the blocks along. And when the humidity gets too high for the temperature, it's going to rain. And such things. Now there's a fundamental difference between these two situations. Here it is said that if a butterfly flaps its wings in Japan, whether and where a storm will hit the United States will change. Some very small differences in the weather today can make big differences tomorrow. Whereas the atomic bomb design, small differences didn't make much difference in the final behavior. The atomic bomb design was stable. This is unstable. We can't predict exactly what's going to happen. You notice when he says it's going to rain in Monterey, it will rain some places, not others. You can't tell just what it's going to rain or how much. And they usually give you 90% chance, which means the following. 90% of the time there'll be a good deal of rain. But if a small amount of rain falls and they predict a clear day, they'll call it clear. And if a little bit of rain falls, they call it rain. They were right. So their batting average is rather higher than you might think, because they have the just right to call, did it rain or did it not? Furthermore, it can rain one place, not another. In this community, I live in what's called the banana belt between the school and the airport. The school was originally selected because it had the best local climate. They searched around the peninsula and found a place where the best local climate was. They built that luxury hotel. Well, they picked the airport where there was the least amount of fog. I live between them. I don't have much fog. I can see fog lots of other places. Other friends are having fog and rain, and we're not. Weather is indeed a very local situation. It's very hard to predict. And this difference between ability to predict and not is everything when you do simulations. It is not easy to do this kind of simulation. It is to do this. Now, both of these must have a property of a great deal of repetition. For each shell, for each time, we calculate what would happen. For each block, at each level, at each time, we calculate. We go through the same thing with many, many repetitions. Now, sometimes in a simulation, you may use repetition from day to day, but if you don't have a great deal of repetition in a computation, you don't write the program. You just calculate it once and you're done. You have to get a great deal of repetition to justify writing programs. And simulation is one of the ways of answering that question. It's very important. I have met a great many of these problems, particularly with the differentializer, which was an analog computer. As you patched up the plug board, you saw the feedback paths, and I looked at those frequently and said, on the paper, Will that be a stable problem or will it not? Because you will find that while this is very easy, this is somewhat unstable, but let's be careful. The weather is stable. Year by year, the weather goes through the same cycles. Although it may vary heavily from moment to moment, there is a stability year by year. But in the long hauls, again, no. We had a sequence of ice ages a while back, which were not like any previous winters before. So there is some inherent stability in the weather year by year, but there's also not a stability year by year. The ice ages tell you the past when man was a very primitive animal in the sense that he did not have much power over nature. He lived in little caves and did almost nothing. The weather changed radically. And man could hardly be the fault. He could hardly have caused the ice ages, yet we had a sequence of them. So weather is a very, very difficult problem, and there are a lot of other problems like that. Social behaviors like that. It's very hard to predict. Now, when I went to Bell Labs in 1946, I soon found myself involved in Nike guidance missiles. They gave me the equations, sent me up to MIT where the big RDA number 2 differentializer was, and told me to do some simulations. The original idea was simple. We will, around a circular track, we will run the missile down at an angle, we'll shoot up like that and try and hit the target. Well, I had an exponential atmosphere. The higher you were, the less density. This is a very simple one for first approximation to do this. I found that if I went this way, got out of the dense air, paid the price of the induced drag bending over, and using wings about 1/3 the size that they gave me, because they'd give me some formulas for changing wing size for drag this and that way. I had formulas to try. That I would in fact get here sooner, and although wings were 1/3 as big, I'd be going so much faster that at closing time I had more maneuverability. Well, I thought for a little while. I'm up there by myself. I got a motel. I was lying in bed about the third night and saying, you know, Hamming, those formulas they must have given you were probably local linear approximations. And if you're going to change the wing size by a factor of 3, those formulas can't be much good. So I phoned down the next morning and he said, yep, come on home. So I went home. They allowed, maybe I was right, they gave me some new formulas because they had to do all the fitting in another part of the process. And when the machine again became available, I went back up and I found, yes, indeed, that the final wing size on Nike were 1/3 as large as the original ones they had given me to start simulating. Furthermore, the trajectory was now vertical. All that equipment running around the circle to point it and level was out, launch everything vertical. And this is the one mistake you'll find, by the way, in Jules Verne's trip to the moon. The story occurs down in Florida, but he has a slant launch, and vertical launch is better. You'll notice we do this all the time. We're always launching vertically when we can, and you'll notice your airplanes taking off from airport. They go up as fast as they can to get up to that thin air and go across, and the last minute they come down. This dense air was terrible. I found it from simulation. But now let me dwell on a point that is bothersome. One point, the solutions came out in about an hour or maybe 50 minutes or something. It's a very slow mechanical machine, and halfway through I had to commit myself to the next trajectory, pretty much. Well, I hung over those plotting boards and looked and felt, why was it slowing down? Why was this, that, the other thing? Until I could feel myself as being that missile. Particularly the second time I went up there, I could feel the induced drags as I bent them over in the closing game. Well, I've asked myself, if those solutions came out 1 a minute, would I not have been so busy shuffling the pieces of paper and looking from one to another, I would have not had the time to acquire the physical intuition as to what missiles were doing? I can't answer, but my own belief is I don't think I would have done as well. I was lucky in that situation to be given a very slow machine and being, I don't want to say compelled, but to give it the time to think very hard about each solution as it came out, instead of shoveling papers and such other things. And I've seen since then many times where simulations are run and many answers are obtained, and it doesn't make much sense. Frequently, fewer answers understood are much better. Now, there's another thing I mentioned earlier, so I won't dwell on too much. They gave me some formulas. They got them out of books. That's exactly what our friend Galileo complained about. He complained back in the early 1600s that instead of looking at nature, they read what Aristotle should do. What Aristotle said should do, and they believed whatever Aristotle said. And he argued that the way to get things going is to look at nature herself and see, or maybe I should say this day of age discrimination, I should say nature himself. I don't know. Anyway, we are in danger by using these simulations and using these formulas I get from other people of going back to medieval scholasticism. And I will bet you in your lifetime you will see a number of these cases in which simulations, well done, don't agree with what happens in reality at all. Because you read the books and didn't look enough. As Galileo said we should, and Bacon and others, we must look at the real world periodically, and we're not. And to give you a dramatic version of it, in the 50s somewheres, I addressed the vice presidents of Bell Labs and president and said, 9 out of 10 experiments are now being done in the lab, and 1 in 10 on my machines. But before I leave, I said, 9 out of 10 will be done on the computer, and 1 in 10 in the labs. They didn't believe me. They knew I was a crazy theoretical mathematician. And later on, they built a bunch of labs because they believed laboratory work was very important. And before they got the doors on the labs, we moved in programmers. Now, those lab benches were very expensive. If you ever look at a lab at Bell Labs, it's expensive. It's got hydrogen, oxygen, everything else, and it's got all kinds of frequency standards, everything laid on. Big soapstone benches, everything. We use them for programmer room. They had overestimated the need of laboratory work. Laboratory work is decreasing. At present, in many areas, 99% of the experiments are done on a machine, and then you go into the lab and run 1 or 2 checks. You search out all the possibilities theoretically where it is, and where are the very interesting cases, and ones which would be crucial. Then you go in the lab and do those few crucial experiments to see that your theory is checking out. We don't do now, or will not in the future, the way you did in the past, and the way the physics books still indicate frequently. Well, you go in and try a lot of things first. No, you calculate a large number of things first, and when you find the very interesting ones, then you go in and measure those to make sure that you've got things right, because our formulas aren't all right. They're sometimes bad. Now, I also advocate very much, as this one. I had a very simple atmosphere. Later on, you'll have to give me a more complicated atmosphere, because you remember the atmosphere is quite strange. It gets hot in places and cold in others and so on. There are various layers of the atmosphere. When you really want to do the final simulation, you're going to have to do that. But of course, the atmosphere is not constant. Some days it's rather different than others, and morning and night is somewhat different, so that in the final simulations, you'll have to ask yourself, how does this missile behave in morning, noon, night, midnight, and such other things? How does it behave in winter and summer? You're going to have to do various atmospheres. But in the beginning, this kind of thing enabled me to do it, because if I ran a bunch of different atmospheres, I'd have gotten confused. Here I had a very simple model, and I advocate, when possible, which generally not, do the simplest simulation you can with the understanding you're going to elaborate it and grow. My better experience is that the people who are in charge know ultimately they've got to have a detailed simulation, so they want a detailed simulation right away. Well, the detailed simulation has so much detail that you can't find the simple things like, well, I'd be better going through, get out of the thin atmosphere. So there's a problem. You'll probably lose by advocating simulating as simple a thing as you can that's got the essential features in. get them under control, and then elaborate and add this feature on this one, until you're ready to go. We did this on space flight, because guided missiles run into space flight. In the early times, we took what we call a stick model of the thing and just ran it up like that. Of course, there's details. And of course, the servos at the bottom swinging around this way, trying to keep the thing balanced up this way to go upward. There's a great deal of detail. And every time I saw a launch, I could see those equations, trying to keep those servos, which are directing stuff out, to keep the thing balanced on its end, rather than have it fall over. You have to do those things ultimately, but don't start. Now I want to talk about another one, a traveling wave tube. This again was a very early one, done on accounting machines in our accounting department. So I have to tell you what a traveling wave tube is. There is a cylinder, hollow, and the wire is wound this way. I put the signal in. Now the signal going along the wire at practical velocity of light does not progress down this very rapidly. It goes fairly slowly. I send in an electron beam faster than this is moving. What's going to happen? The beam and the field are going to interact. Furthermore, what's going to happen? The beam is going to be slowed down. Energy is going to come out of the beam. Where it's going to go? It's got to go into the field. The signal will be amplified. That's the idea of a traveling wave tube. And I was calculating these things, and I realized, you see, when finally the wave is going as fast as the beam, there's no more amplification, you better quit. Because if you go a little further, you get more noise. I realized that I could calculate a taper so that the beam would still be going faster, and I get more energy out of the beam. Furthermore, I realized again what I told you a moment ago about the equations were locally linearizations. Almost always you get local linearizations. And so I said to them, how much of the nonlinear component is present in the linearization? Well, I found in some models the nonlinear component was bigger than the linear component. And there was no use computing. They were collecting more than they were looking at. They weren't happy, in a sense, for me to point this out to them that they made a bad judgment, but it saved a lot of computing. An active, aggressive mind can add a great deal to a simulation. Somebody who just does what they're told adds nothing. Now, one last thing. The beam being charged has a tendency to spread apart because the particles are all the same charge. Negative charge, they spread. So one of the things you want to do is keep the charge of the beam down. Well, you run different beam intensities and you plot results. And I say to them, you know, I can run a beam with no charge on it. I can run down the extreme case, which you cannot do in the laboratory. I can run just by taking out the term of the spread, the interaction between the particles on the beam. In short, I can do experiments which they could not do in the laboratory. There was no way. In a whole set of curves, if this is charge, they could get some points like this. Well, let me try one. I could get that one to tie down the end of the curve. Not this realistic, but it ties down the end of the curve and tells you a lot. And in general, I can, in a simulation, calculate ideal cases that the experimenter cannot build. Not that I want to do those, but it ties down various aspects and tells him where he is about other things. When he knows the extreme case, now you've had enough physics to know that the physicists always talk about ideal gas. There isn't one, but it's a very convenient conception. Physicists have all kinds of ideal things. The same way I can, in a simulation, calculate the ideal situation, and that often sheds more insight and understanding, even if it is not relevant to reality, than reality will. Just think of the role of perfect gas displays in physics. It's the dominant thing. It's the thing you think about, then you say, well, I got to fudge it a little bit because really no gas is perfect. That's the way the mind works. And so you have that. Now, another thing I have to talk about is jargon. If you do a lot of simulations, you will find there is jargon. Jargon is necessary. For example, what is work? If I push like this for a long time and quit, I've done no work because there's been no displacement about the force. On the other hand, you and I know it is work. I get tired. Work was defined in a particular peculiar way so it would fit physics equations. So when you speak of work in physics class, you mean something. When you speak of work among your family, you mean something else entirely. And you see the need for jargon. It concisely says exactly what you mean. So jargon is a necessary thing. But now let me back you up and tell you about the evil. It would appear that during caveman days, cavemen ran around groups something between 25 and 100. I'll tell you why those numbers. If you get too small a group and a couple of vital people die, the group has got no future. If, on the other hand, you have a big group like 100, you begin to exhaust the local food supply. So something we know two are the right numbers, and the 100 comes out from another thing. If I were to check up in this class of how many people you have on your Christmas card list, most of you will find that few of you have more than 100 people. Your Christmas card list, when you get up around 100, you really don't keep track of that many people. During the millions of years of caveman days, you didn't need to, so your mind doesn't do well at keeping track of more than 100 people. Another feature that comes out of that, caveman was apparently competitive. While they stole each other's wives now and then, by and large they defended their territories. They were not exactly peaceful. A stranger was not welcome. And that's right in you. A stranger, somebody who looks different than the people you're familiar with, he's a stranger. Immediate hostility. Well, we now live in cities. We now work in large groups. Our caveman instincts are not appropriate, but we got those instincts. Jargon is a device instinctively used to exclude the outsider. I've seen it again and again. People come in and tell me some jargon when I'm going in. They use jargon around the way because I'm from an outsider coming in from the research department to do something in some engineering. And, you know, theoreticians aren't exactly welcome among experimentalists. Besides, he's a stranger. I had to penetrate their jargon. So one of the first things you do when you get involved in the simulation in some area is you go out and master the jargon. And I can give you an example of what I did. My vice president, who was a chemist, stopped me in the hall one day and said, "Hamming, I want you to serve on the Chemical Abstracts Advisory Panel." I look at him and say, "You know I don't know much chemistry, and maybe you don't know it, but I only think much of chemistry." Even he is my boss. He says, "I'm not surprised," but he says, "They're going to put computers in. They're trying to mechanize computing reviews. I mean, chemical abstracts. And I think there ought to be somebody there who knows something about machines." What can I say but yes? Can I say no? No, I have to say yes. I go back to my office and say, "My God." I immediately call McGraw-Hill, where at the time I had very close relations, and call up the guy there and say, "What is the best organic and best inorganic chemistry books you got?" The textbooks, beginning. He tells me, I said, "Rush both of them out to me." Before I went to the first board meeting, advisory panel meeting, I had read both of them and I had made an effort to master the jargon. I was not going to let those guys beat me by jargon. I knew what they meant. I knew the jargon words. I was not going to become a chemist, but I knew I had to master the jargon. I say the same thing. Jargon is essential. And since I'm on the subject, I have a little spare time. I'll tell you another story very early about that. Early, very early in my experience at Bell Labs, again, I was in West Street where the engineers were, and I was having lunch with the West Street people, the guys who built the machines and such other things, and I was just one of the users. Now, we ate in the cafeteria there, and all during the lunch, they talked about salary raises. We got a 2 dB salary raise this time, we got a 3 dB salary raise this time, and so on. Well, coming from Los Alamos, of course, I know it's half-life. And knowing some astronomy, I know it's magnitude, but they talk that way. Well, as we're getting ready to pick up our stuff and put them on trays, I say, pardon me, gentlemen, but will you tell me whether salary is amplitude or power? Difference, you know, 10 log or 20 log, right? They didn't know, there was no agreement. They both started opening their mouths, they contradicted themselves, and it turned out that they had not known what they were talking about the whole damn lunch. Jargon can confuse yourself. Beware of jargon. That was my very early lesson on the evil of jargon. Not that you avoid it, but there's a good story. It's true. I couldn't have made it up, could I? So, jargon is absolutely necessary. You must master the jargon these people have. And one way to do is go out and get some elementary textbooks and simply read them. And try to find out what the jargon is. And why they do what they do. And what does CGS mean or something else. It's a stupid business. But if you don't, they will not, I will say consciously, but subconsciously, they will exclude you. Because they've got all these damn caveman instincts. They've got them just like you have. They will automatically, without any thinking on their part, exclude you by jargon. They will raise the jargon level on you every time. I've watched it. So you must master jargon when you work with other people doing simulations. I can't say it too much. The first thing you do is get their damn jargon under control and learn a few more things so you can drop a few bombs on them along the way and point out they don't know what they're talking about and you know more than they do. It's a help when you do that. Now, I want to go on to another problem, which is a very, very important one. I've talked and will talk about a certain Navy problem with 28 differential equations. They're all simultaneous, but I'm going to talk as if there were only one. I'm given that condition on the solution. The y's must be less than 1. Well, I calculate the solution. Here is y equal 1. And so I say, the solution is obviously because what they've got is a diode limiting the voltage. Now we've been coding in absolute binary on a 701. Machine jargon is terrible. I say to my friend who wants the problem done, who knows the problem, I said, Dave, we're sitting down, we're going to go over this program to make sure I understand exactly what's what. He said, I said, I am going to run it until you sit down and do it. I come to this point. He says, Hamming, that's fin limiting. The fin comes up like an end stop, and the moment the derivative becomes negative, it peels off. I was absolutely right in my interpretation. He was right in his interpretation. You see how I fell into it? Wouldn't you have, if you're an electrical engineer? What's the difference in the mobility? Quite a lot, right? The simulation would have been wrong if I had not made him, over his objections, go over what we were computing. I thought I knew exactly what those equations were. It's perfectly reasonable what I did. But I was wrong. I came to the conclusion from that one experience that Somebody who understands the problem is going to go over with me what I am computing to check that I'm not making a stupid mistake like that. I doubt that that mistake would ever been caught on any flying some flights to check how well we're predicting things. That's too small. At the same time, it's much too large to be neglected. It's an enormous amount of difference in mobility. For this reason, I say to you, when you have simulations, you cannot turn the simulation over to some professionals and not monitor it with somebody who understands the whole problem. Otherwise, that is waiting for you. Now, it's buried in 28 equations, 28 unknowns. I just pulled it out so you can see that one little piece. And it sure taught me a lesson on that one. And I remind you again, he didn't want to do it. I just was tough and said, Dave, I'm not going to do it. I'm going to run a problem until we sit down and go over it. He said, I know. I'll explain the line by line coding what this dumb absolute binary does. Now, here I'm doing this, here I'm doing so and so, and I'm cutting, reducing y to 1. Now, you can see, if you want to talk abstractly, it's a question solely. Did I substitute that limited value in at each step? Or did I use the old y in here from here? Which y went in there? The limited one at every moment from here or from here? That misunderstanding is very widespread and possible in many, many problems, and many simulations are no good because of those kind of small things that somebody overlooked. There is no substitute for somebody who understands the problem. Now, you shouldn't get the idea that I don't think simulations could work, because I think they're very, very good. Now, sometimes there are other time-dependent ones. I did one which the differential analyzer produced the probability of blocking in the central office. What's the probability of 1, 2, 3, 4, 5, 6 calls to the central office? What were those probabilities? When it got up a certain level, that would be blocking the central office, depending on how they designed it. So I calculated probability distributions. I calculated a lot of strange things. Now, that was a set of infinite number of equations. They had an infinite number of equations for ideal solution. I have, say, 12 integrators. But the equations are very regular. So I look at the equations as being an impedance line, and I simply interpolate for the last two to estimate how to feed back from the one I haven't got. Otherwise, I simply view it as a regular structure, feed it back in, and since the answers were so much loved, I concluded that I must have done the right thing, that with an infinite number of equations and a finite machine, I could solve them anyhow. I ain't scared nothing. There were underwater simulations. A friend of mine had an array down in the Bahamas, underwater antenna trying to detect things, and of course, it was always winter when he had to go down and inspect the thing or make some more measurements. And so I always knew every winter I'd have some more problems of that type. You know how it works. Now, one of the more interesting ones was a jump station. You know those things. They're towers with a horn to another one over there. And it goes on. Well, there are two questions. If I'm going this direction, we'll say. If a pulse, an error occurs here, does it get amplified? If a small error comes in here, does it come out there bigger? In other words, do these ripples get like that? Now, they're stable in the sense that if a disturbance occurs here, although it's here, it will die out. So locally they're stable. But if this disturbance is bigger, this guy sees a bigger one, and he emits a bigger one still. That's a possibility. And for a good word, I call it space stabilization. Was it stable not only at the individual towers, but was a pulse going across the continent going to grow in size or decay? The only ones we can use are decaying ones. So we've got to worry about two stability problems. The stability locally on the amplifiers, which is well understood, and the other, that coupled with the step-by-step going across the continent, was that's going to be stable or not? Well, we did a large number of simulations and found those that would be stable and those that wouldn't be stable, and we built the stable one naturally. We figured out by great many simulations what would happen. And you have to do those kind of things. It's one question. What if we build this? How will it behave? Well, it behaved pretty well. that one. Now, I hope you come up with the attitude that I have. I can simulate anything to some degree. I cannot get perfect results. I am dubious that you've given me the right equations. I'm dubious everywhere. I'm dubious I got the right answers. But the answer to the question, what if, is so important that I cannot not do it. I must do the best I can. I question the equations they give me. I ask for internal checks. I look to see that energy is conserved or this or that. I ask them for, frequently, have you got a special case which you know about? For example, in the same problem here. I may have told you. I took off gravity and lift and asked, would the plane, given a fixed turn, go around the circle, and how well did the circle close in on itself? If it closed in very well, I was accurate. If it didn't close in well, I wasn't. I could make a number of tests like that. And I always believe in doing degenerate cases. But I believe in thinking about those before I set up the programming. I want to set up in such a fashion that's easy, with very little change in program, to run degenerate cases, like to blank out gravity. Just put gravity equals 0. Don't put the G in the program, put the G in a register, which you load, and therefore you can do it. And you got much more confidence that the G was 32.2 or it was 0, because I loaded a register. If I had it in the middle of a program, somebody reached in the program and changed it, I am less sure he got the right 32.2. It might have occurred in several places. After all, if I left it in the program, I might several places referred to 32.2 in several different subroutines, and not had it changed in all of them. I learned a great deal about that and protecting myself to be dubious. On the other hand, we must simulate. There is absolutely no other answer to the problem. Now I'm going to talk in Parent Lecture 20 about a couple extreme cases which on the face of it could not be simulated. I could have proved to you that it couldn't be done. But I just told you I'm going to get answers. And so I did. It cost me quite a lot of time, but I got them. I believe you can if you are determined. It is an important situation you want to simulate. It's very important to your organization that you know the answer to this question, what if, that you can get somewhat satisfactory answers. You can do better than nothing. You can do better than just sitting and say, well, you know, I think the wind's going to blow from the west today. You can do better, but it's a determined character. I've seen a large number of ones abandoned because they thought they couldn't be done, and I've come by later and done it. I've also seen a lot of simulations which were done wrong, and therefore a good idea was abandoned. And I have one standard story which I might as well tell you. Bell Labs was a very long pair of buildings with an arcade, and on the second floor you could look from there to there. It was a tremendously long, straight, wide hall. Well, the bad dream I have is a guy comes to me with a good idea. He wants me to do some calculation or simulation. And for some reason or other, he abandons the idea, and next year somebody gets the Nobel Prize. I have to walk past this guy on the corridor. What do I do? Now, it does not matter if he gave me the wrong equations, or if he gave me the right equations and I calculated wrong, or even if I gave him the right answer and he didn't understand it. I have to walk past that man who had a Nobel Prize in his hand and didn't get it. And you know what a Nobel Prize is to a physicist. It's something better than going to heaven. And you want to think about the matter. You've got a friend of yours and you're going to have to pass him by. Well, that has made me extremely careful about all three things. Is the original problem posed right? Did he give me something wrong? Have I got the right answer? And does the son of a bitch understand what the answer means? Now, you're inclined to not pay attention to that. You're inclined to take the curves because you understand the hand to him that he or she understands what the answer means. Don't believe it. It is quite possible, particularly upper management, to hear what they want to hear. If they don't want to do some project, they will see your curves and see reasons why not to, because that's what they want to see. On the other hand, maybe it's infeasible and they want to do it, and they will see in your curves the reason why they can. It's no different than you, and it's something I think I've said to you before, I'll say to you again. The bigger the rank difference of people, president to a peon, the more there is willful misunderstanding. And the story I have somebody I tell, my vice president was a very good friend of mine. He was very, very good. He was a good friend. He once in a while he'd call me up and ask me to come up to his office just to talk and cry on my shoulder. And I figured part of my job was keeping vice presidents happy. So I went up this time and he said, you know, this guy got a very good job offer over there. And we wanted to keep him. And we thought he had a good future. We might be able to promote him someday to such and such, but he was going to leave anyhow. So they asked me to talk to him. So I had him come up. I talked to him. And he was going to leave no matter what. I couldn't. So I said to him, no, I know you're going to agree to stay a month, but if you want to get the new job earlier, we can understand you want to leave. If you don't want to leave next week, it's all right. Well, the story goes around that since the guy couldn't be persuaded to stay, he was fired on the spot. That is what the vice president said at all, but that's what the man heard. And you can see why. All of you as senior officers need to realize that the problem of communicating what you mean unambiguously to people below is a serious problem. There is a willful desire to misunderstand, because he wanted to hear one thing. He wanted to hear that the boss was mad because he wouldn't stay, so he heard he was being fired. He wasn't. He was saying, well, I'm being gracious. If you really want to leave earlier, we understand. You want to get your new job, it's all right if you leave early. He didn't hear it. It's a problem all the way around. There's a reason why I dwell on it. When you get a simulation answer, the receivee, either higher or lower rank, has a willful desire to misunderstand what the simulation says. And your responsibility is to see to it that the ambiguity does not occur too much. That those who want to use the simulation for proving why the Navy or Army should not do something aren't allowed to get away with it, or those who want to believe that it should aren't allowed. That they all understand just what in hell the damn thing is saying and is not saying. Now that means that when you write the reports up, you read them very carefully over and see how can some son of a bitch misunderstand this one way or the other. They will do it if they can. And as I say again, much of it is a matter of rank. The greater difference in rank, the more there is a closing of the mind and hearing what they expect to hear rather than hearing what is being said. So watch it as a piece of education I'm trying to give you, independent of engineering. It's just plain common sense and you need to know it. Well, next week we'll take up 2 more lectures on simulation. There's a piece of paper around here signing.